Hello and welcome to the NISER lecture series on quantum chemistry by Dr. Arindam Ghosh of School of Chemical Sciences, NISER. So this is the third and the last lecture on simple linear harmonic oscillators. In the first two lectures, we have derived the theory. We have solved the Schrodinger equation, got the energy spectrum. We found the functional forms of the wave functions. We have plotted them. We have discussed them. And in this particular lecture, which is kind of a supplementary lecture, we'll be discussing few more properties of simple harmonic oscillators. We'll be solving a couple of problems on them. But before going to the problems, let's quickly summarize the key points we found in last two lectures. Those key points would be beneficial for our discussion today. So this is more or less everything that we have derived so far. We have got the energy spectrum given by n plus half h nu. Nu is the frequency of oscillation. We can also write it down in terms of h cross omega. N goes from 0, 1, 2 up to infinity. There is no limit on how many energy levels you can have. The reason there is no limit is the potential that goes from 0 to all the way to infinity as either x or q, and we know that q and x are related. As x or q goes to plus or minus infinity, the potential slowly goes to infinity, and therefore any state that we have corresponding to any energy are all bound states. What do you mean by bound state? It simply means that at some point of space, either x or q, the boundary will come where the energy, any particular energy, is going to be less than the potential beyond that boundary we call the classical boundary. It simply means that no matter what the energy might be, no matter how big the energy might be, the state is still going to be a bound state. There is no free state possible for simple harmonic oscillators. So all the states are bound states. There are infinite number of states, and their corresponding energy spectrum is this. The wave functions are having two separate parts that we have discussed in a very detailed way. We have obviously the normalization constant, which is given by this particular expression. Then we have this particular factor, exponential minus q square by 2. We have discussed that this is the asymptotic part, which is responsible for bringing the wave function down gradually to 0 as q goes to plus or minus infinity for each and every wave function, for each and every state. This is the asymptotic part. And then this particular Fn, which is the behavior of the wave function when q is not very large, either this way or that other way, when q is intermediate points, correct? So the behavior of the wave function is given by this particular factor, which is a degree n Hermite polynomial. So depending upon what n we choose, we get a particular energy level given by this formula. Then we get a particular wave function where we have a particular normalization constant. That normalization constant is given by this. Interestingly, the normalization constant is a factor or a function of n. And then we have an nth degree polynomial which dictates the behavior of the wave function in the zone where x or q equals 0. And then towards the high q on the right and high q on the left, this exponential minus q square by 2 wave function takes over, and then it goes to. So this is pretty much all that we have got for simple harmonic oscillators in the last two lectures. We derived each and every these things. So now let's go to the first discussion, the first question on this, and that is related very much with this particular normalization constant that we have. So we have two cases, two different problems that we have discussed in our course that we have listed here. One is definitely the one that we have just done, the simple harmonic oscillator, and the other one is the infinite potential well, the symmetric version of it that we have recently done. Now, if you look at these two systems, these two problems, there are a lot of similarities. For example, in both cases, there is no upper bound of this n that can be. What does it mean? It simply means that in both situations, you can have an infinite number of solutions, infinite number of states that are possible. And the biggest similarity is that in both situations, these states, this infinite number of possible states are bound states. Because you cannot have any energy whatsoever that is more than the potential, because the potential goes to infinity, and therefore the energy is always less than the potential. The difference is that the potential goes to infinity abruptly here at x equals plus L by 2 and x equals minus L by 2, whereas the potential goes slowly to infinity as you go either to the positive x or the negative x direction. It is symmetric potential, definitely. That's the only difference. There are more similarities are there. For example, if you look at the wave functions for simple harmonic oscillators, you can see the ground state is an even function. The first excited state is an odd function, and then again even function, odd function, even function. So therefore, this even function and odd functions are alternating, and we know that here also the ground state is represented by the cosine function, which is an even function. The first excited state is represented by the sine function, which is an odd function. And here also, so 1, 2, 3, 4, 5, 6, 7, it just keeps alternating between these two even and odd functions, and the picture is pretty much like this. The difference, there is another small difference here, is that here the wave function goes slowly to 0. It penetrates a little bit beyond the classically forbidden zone. That is because the wave the potential is not abruptly going to infinity as it is happening here, as it is going slowly to infinity. So therefore it penetrates a little bit. It has certain penetration length, but here wave function will certainly drop to 0 at these two boundaries. But now, why this particular difference is there, which is written here, that why this normalization constant for infinite potential is independent of n. The normalization constant is root over 2 over L. It doesn't have any n. So irrespective of which wave function we are trying to normalize, the normalization constant is still the same. Whereas here, the normalization constant is a function of n. So the normalization constant itself changes as we are going from one particular state to another state. Why this difference is coming? Now you can pause the video here and you can think what might be the reason, or you can just check the solution with me. The solution is as follows. If you look at this part of the wave function without looking into the normalization constant, this is purely oscillatory. A cosine function oscillates between +1 and -1, and the sine function as well. So as n goes to infinity, starting from all the way to 1, the functional part of the wave function and its associated amplitude does not increase with n. The cosine and the sine functions are still oscillating between +1 and -1. Then what's the effect of n? In this particular case, the effect of n is in the argument of the cosine and sine. It simply means that it is changing the frequency only. As n is going higher and higher, the frequency is going higher and higher. Frequency is becoming larger. Whereas here, we know that this particular part, which is the asymptotic part, it is independent of n, no problem. But this fn, which is a polynomial of degree n, becomes a larger and larger polynomial as n goes to infinity. When n really approaches infinity, this fn becomes an infinite series, and we know that when fn really becomes an infinite series, it behaves like e to the power q square. So what does it mean? It means that the functional part of the wave function, again without looking into the normalization constant, the functional part of the wave function, the amplitude of it actually increases as we are going from n equals 1 to all the way to infinity. The amplitude becomes larger and larger and larger. But the probability interpretation says that if you square this wave function and then take the integration from minus infinity to plus infinity, that entire result should be equated always to 1. Otherwise, the probability interpretation will fail. So who will counter this fact that fn slowly becomes a larger and larger and larger polynomial, eventually behaving like an e to the power q square function, which goes to infinity, in fact, as q becomes really large. And why this q becomes large is important here. It's important because as you are going up, n goes up 1, 2, 3, 4, 5, 6, all the way to infinity, you can see that the boundary, the classical boundary, right? The classically allowed zone is becoming broader and broader and broader. So as you are really going into infinity, this particular zone where the particle is allowed to move, the classically allowed zone, will also expand all the way to infinity this side and infinity this side. And then when q goes to really plus or minus infinity, we know that this fn, as it is function, as this particular thing is behaving like this, so this asymptotic part will not bring it down to 0. So the probability interpretation will fail. Then which will save this probability interpretation? The normalization constant. The normalization constant has factorial n and to the power n into the denominator. And as n goes to infinity, these two will bring down the normalization constant gradually to 0, countering the effect that fn is bringing the amplitude up. And therefore, the square of this and integral and the integration over the entire space will still be equated to 1. The interpretation of probability will still hold when this normalization constant is used. And that's the difference. The second question that we would like to discuss is that we will be trying to show that Heisenberg's uncertainty principle holds for simple harmonic oscillator. So we'll be showing that delta x, delta px product is either larger or equal to h cross over 2. But delta x is the standard deviation of x and delta px is the standard deviation of the momentum along x. To solve this, first we need to define the standard deviation of x. Now the standard deviation of x is given by, so the standard deviation delta x is given by the square root of mean square deviation. We can always write like like this, the mean square deviation, which is given by x minus mean of x square, and then take the mean, right? So we have the value x minus the mean of x. This is the deviation. We square it, so it becomes square deviation, and then we take a mean of it. So that's the mean square deviation. That is represented by this delta x square, and if we take a square root of 2, then we get delta x, which is the standard deviation, and we have to show the standard deviation of x and the standard deviation of px. That can be easily be written in this format again to be holding this relationship. Now, in order to get the standard deviation of x, we first need to check the expression. This leads to another expression, which is a known expression, but let me quickly do that in case you are not familiar with it. So this particular quantity, x minus mean of x squared and then mean, can be expanded as x square minus 2 times x and then mean of x plus mean of x square and then take the mean. So this bracket is coming from this bracket, right? And I have just expanded this quantity within the parenthesis in the algebraic form, x square minus 2ab and plus b square, that particular form. And now if we just take the mean again, so what we get here is that the mean of x square, so the first thing that we get is the mean of x square. Then here we already have a mean, right? So we cannot have a mean of a mean, but then we have an x here. So this mean will take this to be another mean of x. So this might be minus 2 times mean of x into mean of x, which is mean of x square. So we'll be getting 2 times mean of x square plus here again. So this is already the mean square. So the mean, we cannot take another mean of a mean, so that remains as it is. So therefore this is going to be like this, and hence this whole thing becomes mean of x square minus mean of x square. So this is mean of x square, and it's the square of the mean of x, right? This is a very well-known relationship, right? This particular factor is the mean square deviation can be written down as the mean of square minus the square of mean. This is a very well-known factors, and we'll be using that here. So what we'll do is that we'll try to find first the mean of x square, and then we'll try to find the mean of x, and then square it, and then we'll take the difference between these two, and that is going to be our mean square deviation. We'll take a square root of that, and then we'll get the standard deviation of x, and we'll be doing the same thing for delta px, and then we'll take a product of these two to check whether this relationship holds or not. So let's try to find the mean of x first. So we'll be doing it in two ways. The first through logic, and the second through proper quantum mechanical steps, right? Logically, mean of x should be 0. Why? That's because the potential is symmetric about x equals 0. So for each and every eigenstate, the classically allowed zone for the particle, where this particle can move back and forth, is symmetric about x equals 0. So obviously, when the territory is symmetric about x equals 0, then the mean of x should be 0. So what we expect from logic is that our mean of x should be 0. Now let's see quantum mechanically we get the same thing or not. Quantum mechanically, if we write to uh, we try to get the mean of x, we should use the formula as follows. So the formula for mean of x, where x here is the position operator x, right? We can use a caret over here, but it's not necessary because we are not using it here. Is given by this formula, where the phi of x is the wave function in terms of x. We have formulated the wave function in terms of q, right? We know the functions are you have a particular polynomial, which are the Hermite polynomial, and then we have an asymptotic decaying function, and we have also proper normalization constant. Everything we have done in terms of q, but here we have to find the position x, right? So if this phi is the corresponding wave function for a particular wave function, for a particular energy wave function, then this is the formula. We know that this particular phi and the psi of q that we have found out are definitely going to be related, and that relationship is going to be a simple one, something like phi x is going to be some constant c into psi of q. What makes us think that this is going to be as simple as this? That's because x and q are related by just a simple multiplication of root over alpha. If you remember that we defined our q to be root of alpha into x, right? So therefore, as this q and x were just related by a constant amount. I'm not telling that this particular constant is a dimensionless constant like epsilon was, right? This alpha is actually not a dimensionless constant. It has certain dimensions, but nonetheless, it's a constant, right? And this constant, as this particular, if you remember this alpha here, the alpha was defined to be m omega over h cross. So this was alpha, right? So we have everything a constant here. We have the mass of the oscillator, which is constant. We have omega, the frequency of oscillation, that is also a constant, and we definitely have a constant here. So therefore, this alpha is a constant quantity given a particular oscillator and a particular oscillation frequency. Hence, this as x and q are related this way, it is quite obvious that a function of q and the corresponding function of x are also going to be related by some constant c. This particular constant is going to be different for different psi depending upon what n. So we can definitely have a different n here, right? We can have an n here if you wish, and this particular constant also might be, we can do it some other time, might be a function of n, but nonetheless it's going to be a constant, and that is good enough for us, because finally you will see that the Cn, whatever it is, this constant, whatever its form might be, is not going to be bothersome for us. So if we just try to calculate the same x in terms of now q, I write down this. This is simple. I just plugged in this relationship in the entire numerator and denominator. We have got this c mod square out here as well, and the c mod square out here. Now these two will cancel. So as I was telling, it really doesn't matter what constant it is, what's the form of this constant is, whether it is a function of n or not, it really doesn't matter, because whatever it is going to be cancelled. So we have got the psi of q. These psi of q are the psi of q that we have previously derived, and the obvious factors that are popping up everywhere. If we just concise this whole thing, we get the following. So we see the mean of x and mean of q are related again by the same 1 over root alpha, correct? So that is quite obvious. And here I have used the index n for this wave functions, because the index n will determine which normalization constant we'll be using, or which particular Hermite polynomials we'll be using. They are a function of n. And if we use the actual form of psi n in mean of x, we get this particular thing. So I have got this particular term multiplied into by itself. So therefore, this goes to q square, not q square by 2. Well, it should be in principle a minus here, right? This minus is missing, so it's minus. And then we have this fn q fn. This part is there. It's a real polynomial, so therefore the fn star is not necessary, so it can be kept as just fn. Here, this particular numerator, sorry, the numerator is not known, whereas the denominator is pretty much known, because we are using normalized wave functions for simple harmonic oscillators. So this particular portion is equal to 1, no doubt about that. The only thing which is not known in this whole expression is this integral. And this integral can be well, this is still not complete, I would say. I must use a dq over here, then only it will be a complete, otherwise it's not complete. Now it's fine. So this integral doesn't have any value at this moment with us. It is not that easy to do this integral, solve this integral, unless we use a particular property. So we'll be using a particular property of Hermite polynomials again, because we know that these are, after all, Hermite polynomials of degree n. So the property of Hermite polynomials that we are going to use now is the following. So this property is a known property. In our case, we have the n and n the same index on both sides of q. So therefore, the case is m is equal to n for us, and it is 0. If m and n are related this way, then we have a non-zero value. But for our case, we have the value for this integral is 0. So if the value of this integral is 0 and this is 1, then irrespective of what an is, mean of x becomes 0. So that is the expected result as well. We expected that mean of x should be 0. I just showed that how mathematically you can get the mean of x. So the next thing that we need to do is that the mean of x square, because together with mean of x square will give us the standard deviation. So let's do that next. So let's try to find out mean of x square in the proper mathematical way first. Then I'll be telling you that it can be also be found in a simpler way, without using any mathematics, just from the logic. So as we have already done the math for mean of x, if you use the same steps, if you follow the same steps, you will reach somewhere here. So instead of root alpha, you'll be reaching to alpha, because it's a q square and not q. So that will bring two root alphas, and they will multiply to an alpha here, and this q square will be here. The rest of the things are going to be very similar. Again, this particular portion is going to be 1, because psi n's are normalized, and to get a value for this integral, we have to use yet another property of Hermite polynomials, and that property is given here. So if you have exactly the same thing with the same index both sides, and then you have a q square. Earlier we have used only q. If you use q square now, the value is this. Now we know that an is given, the normalization constant for the psi n is given by this factor. So if we just use a square of it, then this square root will go away. It is just going to be 1 over this whole factor to the power n factorial n root pi. And that when we plugged in here, and then this same factor is here as well, coming from this integral. So this whole thing is just going to be an n plus half on top and an alpha at the bottom. So what we get is that the mean of x square is just coming out to be n plus half and then numerator and alpha at the bottom. And we can use the value of alpha, which is m omega over h cross. So this simply will become an h cross over m omega and n plus half. So this is the value that we'll be getting for mean of x square. Now this is coming out of a normal math of quantum mechanics to find out the expectation value of the operator x square. Now, if we just use a simple logic, the motion of the simple harmonic oscillator, we can get the same result in a slightly different way. Let's talk about that first before we proceed further. So let's visit the energy diagram once again. Now, these dotted lines are basically the classical limit for the oscillator that it can maximum extend to. The reason I'm calling it a classical limit, because as you know that the wave function is penetrating a little bit into the classically forbidden zone, where if you have this as your energy, right? So classically you should never go beyond this particular x direction, x. This is amplitude for this first level, but you are going a little more. Now, if I just call this particular point, correct? So this particular point, if I call it is x1, and that x1 is the classical limit for the state 1, right? For state 1, that is psi 1 of q. Then in general, I can write down the psi for psi n of q. I have a classical limit, something called x n. Fine. So this particular limit is x2 and x3 and x4 and x5 and so on and so forth. So when the particle is exactly at xn, the classical limit, at that particular portion, I understand that when you have, this is the energy, correct? So this is the energy for the particle, and when the particle exactly here, then this entire energy is potential, because this is the potential energy. So at xn, for a particle in psi n, when this is exactly on the classical limit, the entire energy is potential energy. So what we can write for that particular situation, we can write that n plus half h cross omega, which is the energy for any psi n, right? This is the En. This is equal to half m omega square xn square, because this particular quantity is our v of x, right? And we have already found out that this is the classical limit. So when the distance x is exactly equal to the classical limit, then the entire potential energy is equal to the energy of the oscillator, and I can equate like this. So I get from here solving that xn, let me use the other color that is better, right? So xn square is equal to 2 times n plus half h cross by m omega. So this is the xn square. So classically, this is the maximum x that the oscillator can achieve, or the square of the maximum x. And what's the minimum of the this particular value? The square of x, minimum value for the square of x, minimum value of x squared. That's definitely 0, right? When this particular oscillator is exactly here, then the x square is 0. So the x square, be it this side or the other side, as it is square, so the maximum classical limit is this. So now I'll be using this. I'll be thinking as if my quantum oscillator also follows this particular classical rule, that it cannot escape the boundary given by the classical limit. Although it is not true, you have a very feeble, very quickly dropping wave function penetrating into classical forbidden zone. But I would say that in this region, where there is the classical forbidden region, the wave function is quickly decaying. The particle is actually oscillating between the classical limit. I can pretty much take this approximation, and if we just take this approximation, then we get the maximum value for x square to be this, right? So this is the maximum value for x square. I can write it down that x square max is simply the xn square that we have got here, and x square minimum is definitely 0. So therefore the x square average, which I write down this way, is just the average of these two, and that's just half of the value of this, because that one is 0 and the xn square, so therefore average of these two is nothing but half of this value, and so this 2 will be dropped, correct, and will be coming as n plus half h cross over m omega, which is exactly what we have got from the quantum mechanical way. So we have got h cross by m omega, right, and we have n plus half. So this is our x square average, or the expectation value of x square. Now let's use this mean of x and mean of x square, plugged it into the formula to get the mean squared deviation, from which we can get delta x, which is the standard deviation of x. Let's do that next. By the way, I just realized that this point is not really the x1. This is x0, because this is corresponding to n0. So let me quickly correct the uh, arrow so that it doesn't create any confusion. So x1 is here. So this point is x1, because that is coming from this particular point, which is equal, so this is corresponding to n1, and therefore this point, this is the classical limit for psi 1, and therefore this point is x1. I hope this doesn't create any confusion. Okay, now let's go to the next job. So if we just use the formula that we have previously derived, that the mean square deviation is the mean of square minus the square of mean, and as the mean is 0, so we get pretty much the mean of square only, and we have already found out that the mean of square is h cross over m omega n plus half. So the standard deviation is just the square root of that whole quantity. Let's move to delta px now. For delta px again, we'll be using a very similar situation, right? So the delta px square is just going to be the mean of px square minus the square of the mean px, correct? And this time I'll be using in both situations the shortcuts, the logical way. Although you can find out the quantum mechanical proper way of finding these quantities as well. All you have to do is that you have to differentiate ones. It's going to be slightly more trickier, but nonetheless, it's doable. So as I told, we'll be using the smaller tricks to find out the delta px. That means the trick is that although it's a quantum oscillator, we'll be using the classical picture to find the px maximum and px minimum based on the simple harmonic motion, right? So we know that when the particle is crossing x equals 0, that is the time when its maximum velocity it attains, right? So therefore the px max is going to be at x equals 0, right? And obviously as a classical oscillator goes to a absolute standstill stop when it goes to the classical limit, because it just stops there and comes back, and it goes all the way here, stops here and comes back. So this is not exactly the quantum picture. You know that a quantum particle doesn't just simply stop anywhere, but we have gained enough confidence that if we take this shortcuts, it just luckily works. And that's exactly what we are going to do. So what we would write is the first got the px max, right? So we can write down the px uh, uh, let's say the max px max, right? Uh, let's remove the x. That's going to be useful. So let me start all over again. The x is disturbing me. So let's call it p uh, square max by 2m, and that is equal to the total energy, right? So the total energy is En, and that is n plus half h cross omega, right? So when this particle is moving through this exact x equals 0, fine, then the entire energy is kinetic energy, because the potential energy drops to 0, and therefore the maximum p that you can get is that when this p square by 2m, this kinetic energy term, is equated to the total energy of the oscillator, right? That exactly the same way that we have done for the potential energy. So this is the way, and from there we get the px p square max as the p square max we get is equal to 2m n plus half h cross omega. Um, uh, Now the question is, what is the p square mean, right? What is the minimum? So if you here is the classical picture that we are bringing in. Quantum mechanically we cannot say this, but classically, if you take that approximation, the p mean is definitely or p square mean is definitely 0, because the velocity goes to 0 when it attains the amplitude, right? So therefore this is 0. Fine. And if we just take the average of these two, the similar way we get the uh, p square mean, and that is going to be just n plus half this 2 will go out, because this 2 and well, along with this it will go out. So it's going to be m h cross and omega. So this is m h cross omega. So this is our p square mean. Now we have to find the mean of p. Again, we'll be using our logic, and we know that as the particle is moving back and forth in both directions, correct, and it is quite symmetrical. It is not that difficult to find out, or difficult to imagine that the mean of P is going to be zero, correct? Because it has equal probability of moving this direction and equal probability of moving exactly opposite direction. So it's going to be zero. So we can use again our logic, and we can write down that the mean is going to be 0. And if the mean of P is 0, so the square of it is 0 as well. So we have already got the mean of square, and we have got the square of mean, correct? So now if I just take the difference between these two, I get the delta p square, correct? So we have got a delta x square here. We get a delta p square, and that is just going to be equal to this value, right? Because this is 0 anyway. So delta p square is just this. Now, if we have delta p square just this, then we can take a square root and we can find out the delta p x, right? So let's combine everything together. Fine. So let me write it down here, just for the sake of um, completeness, that we get the delta p square to be equal to n plus half m h cross omega, and therefore if I just use the just a minute, if I just use delta px, I'm bringing the x again here. If I just use the delta p, this is simply the same as the n half, right? So I just as a square root of it. So I just get n plus half m h cross omega, and then we have a half. So we have got delta x over here, right? And we have got delta px over here, and all we have to do is that we simply have to multiply them, right? Let's do that. So I have just multiplied the delta x and delta px that we have obtained in so far. This is delta x and this is delta px. I have just multiplied them, and we get n plus half h cross, because this m omega cancels, right? And this simply means that for n equals 0, right? So we have the index n goes here as 0, 1, 2, etc., etc. So for n equals 0, which is the ground state, right? We get h cross by 2 exactly, because n equals 0. So we get for ground state delta x delta px is equal to h cross over 2. But for any other n, where n is either 1, 2, 3, or whatever it is, it's going to be more than h cross over 2. So therefore, this is equal to n0. And then for if n positive, any n positive, we get delta x delta px greater than h cross over 2, right? So combining these two, we can write that delta x delta px is either greater than or equal to h cross by 2 for any state of simple harmonic oscillator. So let me conclude this chapter on simple harmonic oscillator here. This entire thing is spanning over 3 lectures. I shall give the links for lecture 1 and lecture 2 in the description below. There are many other things that can be done in this particular topic on this particular topic. But for the time being, let's conclude this thing here. We have used lecture 1 and lecture 2 for formulating the theory of it. We found the theory of simple harmonic oscillators, its wave functions, energy eigen values, and the properties of the motion in lecture 1 and lecture 2. And the lecture 3 is more or less a supplementary lecture which dealt with a few more properties of simple harmonic oscillator and a few problems. That's good enough for today, and that's good enough for simple harmonic oscillator. It's a bye-bye from me.